So in today's class, we will look at some important observations about the zeros of linear phase FIR. We will start by looking at the symmetric cases, which are the types 1 and 2 respectively. And now for the types 1 and 2, you can write h of z is equal to sigma n equal to 0 to m minus 1. H of m minus 1 minus n is raised to minus n because of the symmetry of the filter coefficients. Now, because of the symmetry, you have h of n is equal to h of m minus 1 minus 1. Now, if I put m minus 1 minus n is equal to k, then you can write n is equal to m minus 1 minus k, and this equation becomes sigma k equal to m minus 1 to 0. H of k is raised to minus m minus 1 minus k, which is because it's a summation, you can interchange the limits. You can interchange the limits of the summation. So this becomes sigma k equal to 0 to m minus 1. H of k, I'll expand this as z raised to k into z raised to minus m minus 1. Since summation is over k, I will take z raised to minus m minus 1 outside. So what will remain is therefore sigma k equal to 0 to m minus 1, h of k z raised to k. Now observe this equation carefully. Sigma k equal to 0 to m minus 1, h of k z raised to k can be written as h of z raised to minus 1. Because you know that sigma k equal to 0 to m minus 1, h of k z raised to minus k would have been h of z. So in place of z, you have now z raised to minus 1. So therefore, this reduces to z raised to minus of m minus 1 into h of z raised to minus 1. So this is the same polynomial h of z, except that z is now replaced by z raised to minus 1. For example, if you had 1 plus 2 z raised to minus 1, now h of z raised to minus 1 would be just 1 plus 2z. Okay. So let us go to the whiteboard and try to explain the rest. So now you have h of z is also equal to z raised to minus of m minus 1 into h of z raised to minus 1. This is what we have to write now. Now suppose if you have a 0 at z equal to 0, z equal to z naught. So z naught is a 0, which means you say 0 implies that h of z naught is a 0, which is equal to, as per our equation A, you can write as z naught raised to minus and minus 1 into h of z naught raised to minus 1. So which means this equation has to vanish to 0. Now, which means that this has to vanish to 0. So this is equal to 0. So which means that h of z naught raised to minus 1 is equal to 0. Or it implies that z naught raised to minus 1 is a 0, right? So which means if z naught is a 0 will definitely mean that 1 by z naught is also a 0. So this is the first observation that we are using. Now the same argument will apply to types 3 and 4 also. Therefore, for types 3 and 4 also you have the same argument that if z naught is a 0, then z naught raised to minus 1 is also 0. Because for types 3 and 4, the difference is that they are antisymmetric, and therefore we can write h of n is equal to minus of h of n minus 1 minus n, and you will end up with a negative sign here. But so the argument that if z0 is a 0, z0 raised to minus 1 is also 0 is applicable for types 3 and 4 as well. Now we are interested in looking at the positions of the zeros. If z0 is a 0, whether we can locate the other zeros. Now, thus if z equal to z1 equal to r e power j that is 0, then you see that for linear phase FIR filters, you have z equal to 1 by z1 equal to 1 by r e power minus z theta is also 0, which we have just proved. Now, if h of n is real valued, which means that all the filter coefficients are real valued, and if you have a complex root of this h of n, if you have a complex root of this h of n, it means that its complex conjugate root also should exist, right? So otherwise the filter coefficients will not be real value. So if 5 plus 3j is a root of h of z, and if all the coefficients of h of z are real, which means all the samples of h of n are real, then its complex conjugate, which is 5 minus 3j, also should be a root of the polynomial h of z. So complex zeros, if they exist, they will exist in conjugate pairs when h of n is real valued. So that is to be emphasized. When h of n is real valued, complex zeros exist in conjugate pairs. Now, you already have seen that if r of e power j theta is a 0, then 1 by r e power minus j theta is also 0. And now, if r e power j theta is a 0, for a real valued h of n, it is essential that r e power minus j theta is also 0. And therefore, its conjugate also will be 0. So, which means the 0 constellation now will consist of the quadruplet r e power j theta, 1 by r e power minus j theta, r e power minus j theta, and 1 by r e power plus j theta, which we will mark in the whiteboard here. So let me mark the unit circle to emphasize the positions of 1 by r and r. So I'll mark the unit circle here. So let me mark r here, which is greater than 1. So this length is r and this is theta. So r e power j theta will also mean that its conjugate r e power minus j theta. So this is minus theta. So this is r e power minus j theta. This is r e power j theta. So these are two zeros on the of the polynomial h of z. So if r e power j theta is 0, then you will know that 1 by r. So 1 by r will be less than 1 because r is taken to be greater than 1. So this is 1 by r. This length would be equal to 1 by r e power minus j theta. So this is 1 by r e power minus j theta. So we'll mark it using a different color. Mark this up to this. So this is 1 by r e power minus j theta. And likewise, 1 by r e power plus j theta is also 0. So this is 1 by r e power plus j theta. 1 by r e power plus j theta. So the 0 constellation will now consist of a 0 here, a 0 here, a 0 here, and a 0 here. Which means if you have a 0 at this location, its conjugate will also be 0. Its reciprocal is a 0. The reciprocal of this also is 0. So this will consist of 4 zeros in the constellation, 0 constellation. Now, this is only when h of n is real valued, as I have previously mentioned. Now when h of n is real valued and if the complex zero is on the unit circle. So let us see what happens if the complex zero is on the unit circle. So when the complex zero is on the unit circle, so let us look at a different case. So I will now mark a unit circle here. So this is the unit circle. So this is where I have a complex zero. Let this be a complex zero. Since it lies on the unit circle, I can mark this as e raised to j theta. And now this is e raised to minus j theta, which is conjugate. Now e raised to j theta, its reciprocal also will exist as a zero. So which means I have a second zero at e raised to minus j theta. And e raised to minus j theta has a reciprocal as e raised to j theta. So there will be double zero at this position as well. So there are a pair of there are two zeros at e raised to j theta and there are two zeros at e raised to minus j theta. Okay, is it understood? So now we move on to the third observation, which is when the zero is real and not on the unit circle. So for example, the zero could take a value of 5. So which means its angle, that is theta equal to 0, and the 0 could take a value of, say, let's say minus 3, which is when the angle is equal to plus 5 radian. So if the 0 lies at, let's say, plus 5, then you will have its reciprocal at 1 by 5. So if plus 5 is 0, then 1 by 5 is also 0. Likewise, if minus 3 is a 0, minus 1 by 3 also will be 0. So if a 0 is real and not on the unit circle, then there are a pair of zeros located at r and 1 by r, that is for theta equal to 0, or at minus r and minus 1 by r, which is for theta is equal to plus 5. And finally, if you have a 0 at z equal to plus or minus 1, so in that case, if you have a 0 at z equal to plus or minus 1, then you will have its reciprocal and its conjugate at plus or minus 1 itself. So if plus 1 is a 0, then its reciprocal is also plus 1, right? Its reciprocal is also plus 1. So you can have a 0 at, you can have a double 0 at z equal to plus 1. Likewise, if you have a 0 at z equal to minus 1, you will have a double 0 at 0 equal to at z equal to minus 1. Now we move on to another observation, which is very important about types 2, 3, and 4, which is about the value of h of z at z equal to plus or minus 1. So we look at a specific example where we look at the values that h of z take at z equal to plus 1 or z equal to minus 1. Now for types 1 and 2, you can write h of z equal to z raised to minus minus 1 h of z raised to minus 1. For types 1 and 2, you can write h of z equal to z raised to minus and minus 1 into h of z raised to minus 1. Now let us put z equal to minus 1 and see what happens to the equation. So which means we can write h of minus 1 is equal to minus 1 the whole raised to minus m minus 1 into h of minus 1. Now you know that for type 1, the length of the filter is odd. So which means m is odd. For type 1, m minus 1 is therefore even. So minus 1 raised to minus of m minus 1 will therefore reduce to 1. For type 1, therefore, you have a simple plane equality which states that h of minus 1 is equal to h of minus 1. So you don't get any information from that. You just have a plain simple equality. So you might have a 0 at z equal to minus 1, or you might not have a 0 at z equal to minus 1. You cannot make any conclusion about that. However, for type 2, you have h of minus 1 is equal to minus 1 whole raised to minus of m minus 1. Now you see that For type 2, m is even, so m minus 1 is odd. So minus 1 the whole ratio minus of m minus 1 therefore returns a negative 1 value. So for type 2, this equation becomes h of minus 1 is equal to minus of h of minus 1. Now this can be true only if h of minus 1 is 0. So this implies that h of minus 1 is equal to 0, or which means that you have a 0 at z equal to minus 1. So this is important. Type 2 systems must have a 0 at z equal to minus 1. So for type 1, you may or you might not have a 0 at z equal to minus 1, which is for you to find out. But for type 2, you definitely have a 0 at z equal to minus 1. Now for types 3 and 4, h of z can be written as minus z raised to minus m minus 1 into h of z raised to minus 1 because of the anti-symmetry of the filter coefficients. Now, therefore, if I put z equal to 1, you can write h of 1 is equal to minus of 1 raised to minus m minus 1 into h of z raised to minus 1. So 1 raised to any number is a 1 itself. So you can write this as h of 1 is equal to minus of h of 1 for both types 3 and type 4. So h of 1 is equal to minus h of minus h of 1 for both types 3 and type 4. So what does it indicate? For types 3 and type 4, you should have a 0 at z equal to 1, as otherwise this relationship will not be satisfied. So for types 3 and type 4, the system will have a 0 at z equal to plus 1. And now finally let us put z equal to minus 1 for the type 3 and type 4 equation for antisymmetric FIR filters. Now you see that for type 4 system, this reduces to a simple equality as we had discussed for type 1 system. Type 4 system simply says that h of minus 1 is equal to h of minus 1. So you don't have any information from that. You may or you might not have a 0 from there, which is for you to find out. But for type 3, you can write this as h of minus 1 is equal to reduces to h of minus 1 is equal to minus of minus 1 whole raised to minus and minus 1. So you have a minus 1 into minus 1 raised to minus and minus 1. So which you can write as minus 1 the whole raised to m into h of minus 1. Which means that for type 3 systems, you definitely will have a 0 at z equal to minus 1. For type 3 systems, you will have a 0 at z equal to minus 1. So to conclude, we have looked at the zeros of types 1, 2, 3, and 4 filters. And you have seen that if z equal to z1 is a 0, then its reciprocal is also a 0. And now you have also seen that when h of n is real valued, or which also means that h of z is having real valued coefficients, then complex zeros exist in conjugate pairs, and now will be the quadruplet r e power j theta, 1 by r e power minus j theta, r e power minus j theta, and 1 by r e power plus j theta. And now we have looked at specific cases when the complex zero is on the unit circle, and the specific case when the zero is real but not on the unit circle, and the specific case when the zero is real and lies on the unit circle. Then again, we had looked at some important observations of type 2, type 3, and type 4. And you had concluded that for type 1, you cannot make any specific conclusion about the 0 at z equal to minus 1. Now, you may or you may not have a 0 at z equal to minus 1 for type 1, which is for you to find out. You simply have to substitute z equal to minus 1 and see whether it is reducing to 0. But for type 2, you can definitely say that there is a 0 at z equal to minus 1. For types 3 and 4, you see that there is a 0 at z equal to plus 1. And for type 3 system, you also see that there is also a 0 at z equal to minus 1. Okay, so that concludes today's session. And now what remains in linear phase FIR filters is its realization. So we'll see how this can be realized, how the direct form or maybe the transverse to direct form can be simplified to implement a computationally more efficient uh, implementation for the FIR filters. So that will be all. We will meet in the next class.